Hello, guys, and welcome to today's session. We appreciate your presence and the creation of time to join this call. We hope that we will get to learn from this call and share experiences as well, and continue to support one another, handhold one another, and learn from each other's experiences as well. So, my name is Brian Aholi. I'm gonna give a brief overview of weeds, who weeds is, and then I'll introduce the speaker of the day, who is Samuel Kigo, and then Samuel will take over from there. So a brief overview of Weeds Kenya. So Weeds Kenya is the Kenyan chapter of the Women in Data Science Worldwide initiative dedicated to advancing the Weeds mission locally. So like how global counterpart Weeds Kenya is committed to empowering women to reach their full potential in the field of data science. As Weeds Kenya, we strive to elevate and celebrate the exceptional work of women in data science within Kenya, fostering a community of respect, collaboration, and visibility. So Weeds Kenya plays a crucial role in addressing the underrepresentation of women in data science, ensuring that their voices are heard and their contributions are recognized through access to educational programs, resources, and networking opportunities. WIDS inspires, educates, and supports women, and by extension, men as well, in their journey to become leaders in data science. So our goal is to contribute to the global WIDS mission of achieving 30% representation of women in data science by 2030, thereby creating a more inclusive and equitable future for all. So as we continue to build a strong and vibrant data science community in Kenya, WIDS Kenya remains dedicated to reducing barriers to entry and career success for all data science enthusiasts within our community. And we are committed to ensuring that everyone is fully integrated and represented in all areas of data science, including AI, and shares equally in decision making, economic prosperity, and opportunity. So this commitment is reflected in our regular data drills, this being one of them, where we focus on hands-on learning and skill building. So at this juncture, allow me to introduce our speaker of the day. So it's my pleasure to introduce to you Samuel Kigo. He's a seasoned senior data scientist with over 5 years of experience at the forefront of data-driven decision-making across diverse industries, including banking, sales, credit, finance, and telecommunications. Samuel is a recognized expert in machine learning, predictive modeling, natural language processing, focusing on creating transformative solutions that deliver tangible business outcomes and impact. In addition to his practical experience, Samuel is an accomplished author. His recent work, published in the Scientific Reports Journal, delves into cutting edge techniques for pricing strategies, market trends, and decision making processes in the diamond industry and related fields, showcasing his ability to apply advanced analytics to real world challenges. We are excited to have Samuel share his deep knowledge and insights with us today during this week's data drill session. So let's explore the captivating world of classification with Samuel Kigo. I hope we will enjoy the session and learn from his experiences as well. So much welcome, Kigo.
So thank you, yes, Brian, and everyone for making time to join the call to learn with me, explore more about the classification. It's one of the areas in machine learning.
Are you sharing your screen, Kigo?
No, no, no. I thought I could share the entire screen. Can you see my screen, the slide?
Yes. We are seeing your email, so you can open the slide.
I'm on the slide. So can you see my entire screen?
Yeah,
So then I go to slide. Can you see my
yeah.
screen?
Can see the slides. Yes.
Okay, thank you. So we'll learn about classification modeling is a type of supervised machine learning, methods. In machine learning, we have two broad, supervised and unsupervised. So classification is a supervised method whose goal is to predict the categorical class labels of new instances based on past observations. And its application is not limited to the list here, but you have healthcare, where it can be used to predict presence of disease and preventive methods to be proactive in treatment. In the areas of finance, um, classification could be applied to check fraudulent transactions. This is segregating them from the legitimate ones. And then in marketing, um, there's segmentation of customers, but in itself, that is unsupervised. If you carry out a test like RFM, which is the recency, frequency, and monetary value of a customer, which is unsupervised, you could augment that with a supervised technique. For example, you can take the output of the RFM and make it input into a classifier, try make it predict the customer lifetime value, the CLTV. Those are some of the applications, but for today's session, we are going to get our minds into the world of healthcare, and I'll be trying to classify the fetuses. Fetus, I believe, is unborn baby in the womb.
Hello, Kigo. Sorry for interruption. I think your audio is not stable. I don't know whether it's from my end or even other audience experiencing the same.
Sorry about that. How about now?
You can go on so that we can tell.
Okay. So sorry about that. So I'm saying for today's session, we'll be delving into the world of healthcare, and the case at hand is assessing fetal health. Uh, Fetus is an unborn baby in the mother's womb. So we'll be trying to classify the status of fetus. It could be a health that is normal, could be pathological, and other classifications. I don't know if I'm clear in terms of audibility. Can you hear me?
It's much better.
Okay.
I think you will just raise your voice.
Okay. The case at hand is a fetal health analysis. And as I've said, the health of a fetus in the mother's womb through a scan, that is CTG, will be classified as normal. That's a normal fetus. Suspect, there's a challenge, and pathological. The fetus is not in good shape in terms of health. Just to lay the foundation of our case today, so the objective is to unlock the power of cardiotopograms. In this session, we'll be just using the initials, CTG. So cardiotopography is a technique used to measure fetal heartbeat and uterine contractions during pregnancy. And from the observations, the fetus is classified to either being normal, suspect, or pathological. And for you to do that, we are going to use a classifier. The precision of ultrasound technology to safeguard fetal and maternal health. That will be the foundation. Then CTGs with their cost-effective monitoring capabilities offer a proactive shield against infant and maternal mortality. Then, that is the overview. Our objective today will be to conduct an in-depth analysis of vital fetal indicators, focusing on various features and their interconnected relationships, as well as classify fetal health to prevent um, child maternal. Um, the methodology that we are going to follow in this use case, we are going to perform data processing, then do exploratory data analysis, that is EDA, and then we build model or candidate models, and then evaluate the success of our use case based on that. Any data science work starts with data understanding. So the data sets that is going to be used for this use case is obtained from Kaggle, which is open source. I will refer you to the same data set if you may want to do some analysis. So the data set has a total of 22 variables about the fetal health status. Then, out of these 22 variables, 21 are predictor variables, 20 of which are numeric, and one is categorical. The response variable, of which we refer to as target, is fetal health. So fetal health has three categories, as I've said. We have normal, suspect, and pathological. I have tried to group the data set in various clusters so that we understand what each group does in terms of predicting the fetal health status. The first set of variables contain fetal heart rate. This is the heart rate of fetus, which measures the heartbeat or the heart rate of the fetus. Then on which we have a baseline. Baseline is what is normal for a normal fetus. Then we'll be trying to get the deviations from the same. The baseline will be the reference point for assessing deviations, accelerations, or decelerations, which is the number of temporary increases or decreases in a fetal heart rate, variability which reflects the adaptability of the fetal nervous system. The second set of predictor variables is about fetal movement, which measures the number of fetal movements per second in the uterus, where active movements indicate fetal well-being, and the reduced movement might signal a problem. The third set of predictor variables will focus on number of contractions in the mother's uterus per second. So this is basically the foundation in terms of the data that you're going to use. And from this point, I'll take you to the notebook and run through the process of getting to our model and the prediction. So can you see my notebook?
Yes. Could
Okay.
you kindly increase the legibility of the font?
Okay.
If you do a control plus, will it increase?
Yeah. How about that?
Yeah, from my side that's much better. Yeah, perfect.
Okay. Thank you. So this use case is
Also, sorry about the distraction, but you see that pop-up which says stop sharing or hide? Yeah, that one. Thanks.
so you want us to hide. We have hidden. Thank you. The use cases are predicated on the urge for UN to reduce the instances of, fetus dying in the mother's womb, and sometimes that may cause even the mother to die. That is what these use cases are predicated on. So reduction of child mortality, just taking you through the context, reflected in several of the UN nations Sustainable Development Goals, and is key indicator of human progress. The UN expects that by 2030, countries and end preventable deaths of newborns and children under 5 years of age. with all countries aiming to reduce under 5 mortality to at least as low as 25 per 1,000 live births. This is what drives this use case. Do not read the rest. About the data set contains 2,126 observations of features extracted from PTGs, which were then classified by 3 expert uh, doctors into 3 classes: normal, suspect, pathological. Uh, this cadre of medic is a physician that specializes in delivering babies and caring for people during pregnancy and after they give birth. They treat medical conditions unique to pregnancy and perform surgeries related to labor and delivery. So for this notebook, I'm not going to run the chunks because this will spend, I'll spend like 20 minutes, waiting for them to run. So I've done that before, so I'll just walk you through. These are some of the libraries that I am using for this use case. For you to have a view of the data has 22 columns. These are variables. This is just some few lines. You can see the variables. For example, you have baseline, which we say is the reference point. When you say there is high acceleration or low, you have a baseline, which is the baseline value. Then you have accelerations. This is another variable, a predictor variable, fetal movement. We will have a look below here so that we have an understanding of what we are doing, which is desirable for any data science work. So about the baseline value, this is the baseline value for fetal heart rate, FHR. The baseline fetal heart rate measures, it is measured in beats per minute. Then, why does it matter? It provides a reference point for assessing deviations. Why is it significant? Abnormalities may indicate fetal distress, and this calls for medics to be proactive and try to assess the situation and give it some medical attention. Then another group is aberrations. This is number of temporary increases in FHR. Why does it matter to this particular use case? Alterations are positive signs showing fetal responsiveness. More of it is reassuring. More alterations, they are reassuring, meaning the healthy status of the fetus is reassured. About the movement, this is the number of fetal movements per second. Active movement indicates fetal well-being, while reduced movement might signal a problem. Then there are variables that are based on the uterine contractions of the womb. So the number of contractions in the mother's uterus per second. Then why do they matter in this use case? Contractions play a role in labor progress. Normal pattern is where contractions become more frequent and intense during labor. Significance, abnormal contractions affect fetal oxygen supply. We have the variations, temporary decreases in FHR. Why do they matter? They can indicate fetal stress, excess or reduced amount of the same. Early deceleration associated with contractions are usually benign, late or variable decelerations need attention. So this is just an understanding of the data set that you are dealing with. And when we come to dealing with those variables, it's advisable that you understand your data. Then we have variability. This is fluctuations in FHR. Why does it matter? Variability reflects the adaptability of the fetal nervous system. Moderate variability is normal, reduced we signal some distress. Then the histogram is the histogram of these measures that we have highlighted above. It is in terms of the shape. If you have like baseline, what is the shape of that histogram if you plotted it? Whereby if it is negatively skewed, we'll give it -1. A normal histogram will be 0, and a positively skewed histogram will be 1. So in a sense, this will be a categorical variable with 3 categories. Why does it matter? Understanding the histogram tendency helps us identify patterns in the data, such as whether it's centered around a specific value of Q. And this will be very important when you're dealing with variables, when you're feeding your model with this variable. The algorithm will have something based on the centrality of the data or the distribution of the same. We are having a look at data using missing a node with a Python library. Just try and check if you have any missing nodes in the data. And we have 2021-26 observations, and we see all the variables have all the data points. No variable has less than 21, 26. So meaning we do not have any missing less in our data set. Another thing, this is the initial stages of analysis, which is pre-processing. We are checking the type to see if all the variables conform to the right data types. And this is important for understanding and for modeling. For example, we see here the last variable, 21, it's being assigned an integer, but we know it's not an integer. Fetal health, as we say, is the class of the fetal characteristics, normal, suspect, pathological. So this one we may need to change. Another variable we have said is categorical is the histogram. So we also need to check if it has been given the right data type. I can see here histogram tendency is assigned integer. We know it's not an integer. Is the dimension of a histogram being skewed or not skewed? So it has three classes. So we assign them the right data type, both the fetal health and the histogram tendency. And then another thing is checking the duplicates. Do we have duplicates in our data set? And from this check, we have 13 records that have been repeated in our data set. So they are of no use, and they will increase our computational expense. So we need to clean them up. And that particular function is meant to do that. We drop them, we map them and then drop them. For example, you see this, for example, baseline value. Another one is these records. This is again on baseline value. Variations, so they are repeated and they are of no gain in our analysis. So we are going to change them or to drop them. So we drop them and confirm the data set that is left still has some duplicates, which we do here. This confirms that we have 0 duplicates. Another thing is outlier detection. So outliers, what do they do to the model? When you model and your data has outliers, they tend to draw the line of best fit towards them. And whatever results you'll be having probably will be inflated. They'll be spurious, they'll not make sense. So you also need to think about it. And on the same point about outliers necessarily do not mean incorrect data points. And that's why if you intend to remove them, you have to ensure that you understand that the outliers were due to errors. If not, you may not want to drop them. You keep them because they are real records. So how do we check outliers? Simplest way is through the box plot. So box plot has actually one major element, which is whiskers. The box plot tries to assess the centrality of your data in terms of the median. It constructs 2 levels. On the extreme side, through the whiskers. A whisker on the top of the box plot shows the upper fence. On the lower side, that is the lower fence. Points beyond lower side and upper side, or lower fence and upper fence, the outliers. For example, we see that this variable here, let me try to see which one it is. This is a histogram variance. It has some extreme outliers, a point like this one. So these are some of the points that are outliers. We may need to trim them, but we need to think about how to work with outliers because necessarily we just don't do them. Another thing from the box plot is that our data is not on the same scale. So that calls for standardization, which we interact with later. About outliers, so we have seen we have some observations which are outliers. These are values outside the box plot discussed. At this point, we will not remove them because we are not sure whether they are correct observations or they are underlying data collection issues or sampling methods that are used here. And the removal of outliers is a judicious process, and they can only be removed if indeed the occurrence is due to error. So in this particular case, I choose to work with them because I'm not sure whether they are correct. We have talked about feature scaling. You are trying to bring the features on the same level so that you do not have features that overshadow the existence of other features due to their magnitude in the data set. So you bring all the features on the same scale, and in short, you are trying to scale them such that they are between, they have a mean of 0 and variance of 1. At this point, if you may be having any questions, maybe you may want to.
Yeah, there's a question from Paminda.
Okay.
He says, kindly clarify box plot, whisker, upper fence, and lower fence. Perhaps just demonstrate using one of the box plots, one of the variables. And then I think someone else has raised their hand. After you are done with that, then we will give them the chance to ask the question. That's Ian.
Yeah,
Thank
so um, basically, box plot is based on what I try to give a simple explanation. Let's say you have 1 to 100, and then you divide your data into 4 quarters. You have 25th, you have 50, 75th, and 100 in terms of the quartiles. Then, if you have a point that is above 100, I use 75, 75th percentile and 25th percentile. What you compute is what we call IQR. Maybe have a like chart on that, which is the quartile range. You want to take points that are greater than the interquartile range. The 75th, for example, the upper fence will be the 75th percentile, and you want to give yourself some allowance, so you multiply by IQR, interquartile range. Or in very simple terms, based on the median, which points are an outlier? If in this session we have someone who is 90 years old, sorry for using that example, that could be an outlier because maybe a median age, for example, is 28 or 30 or something like that. I don't know if that, on the bare minimum, responds to your question.
So, yes, perhaps a demonstration on any of those box plots displayed for any of the variables to just demonstrate, okay, where is the median? If you are looking at at a particular box plot, where is the median and where do you anticipate the 75th percentile to be, which is the upper fence and which is the lower fence,
Okay.
on
Okay.
what you're just displaying right now on the screen.
Let's have a look at which variable. Yeah, this variable here, which is
Histogram width.
histogram width. So for this variable, this is the median. So based on the median, we have a fence here, and we have a fence here. So this fence is the upper bound, beyond which if you find a point, then that point is an outlier based on the median of the majority of the values or observations for that particular variable. On the lower side, you have the lower fence here. You do not expect, this is below the minimum expected value for this variable based on this median. So this is the median. These are the quartiles. And then you have a fence here. This is the maximum we expect. You have a fence here, which is the minimum we expect. So this is the lower fence. This is the upper fence. So this point is over and above the upper fence. So that is an outlier. We do not mean that is an incorrect or a wrong observation, but it is outside the norm.
Paminda, is that clear?
Very clear. Thank you so much.
Thank you.
Box
Ian,
plot and whisker.
So
is the same
whisker
thing.
is this thing. Whisker is what is moving from the quartile to the fence. So on the top of the whisker, you find the fence. So this is the whisker. This faint line here is the whisker. At the end of the whisker, you have the fence. So any point that is outside the whisker, the upper side of the whisker is an outlier, both on the lower side and on the upper side.
Thanks. Ian,
Thank you so much, Kigo, for such a great presentation. I have a question in regards to the clarification on the box plot. If you compare this diagram, the box plots that I'm seeing and the normal ones for the bars and whiskers, you realize that they clearly elaborate or they clearly show various percentiles. So I
Yes,
just wanted to understand, like for your case here, I can just be able to know to see the outliers and also the 50th percentile. How are we able to break them down from the 25th percentile, 75th percentile? Yeah,
yeah, yeah, that's a
25th.
very good, yes, that's a very good question. For the basic box plot, you have a median and you have two whiskers, or maybe one whisker, depending on the distribution of your data. But this one is an improved box plot, whereby other than just showing you the median, it also shows you where the majority of your data points falls. And for example, for this one, the majority of the data points are, if you map it on this is y-axis. So they will see the majority are between around here. I can't get the figure, but maybe 20 to around this one. This is maybe, for example, 75. So the majority of your data points for this particular variable, for example, ranges between 25 and 75. And then you have another data points still within this variable that are on this percentile. And then you have very least values around over 100. So this is just an improved version of a normal box plot for you to just have an inward look of what is happening in terms of data points for a particular variable. But maybe next time we just use the basic the, box plot, which has median and whisker.
and
Oh,
perhaps maybe if you allow Kigo to add on to your response, is that now considering the number of variables we have and the display space you have, there's another alternative whereby you can visualize each variable on its own box plot and give labels, clear labels to demarcate where the 25th percentile is, where the 75th percentile is, and so on and so forth. There's that flexibility. And these are some of the things as we progress. And I also challenge you guys to take some time out of this to also now do your independent research and yeah, some exploration as well. Ian, I hope that is fair.
yes, that is fair. Just the last question. Sorry for taking much of your time. You mentioned about dropping the duplicates values. I had this one concern, considering that in our use case scenario, we are looking at mothers, pregnant mothers who are coming in with children, and we are able to take the fetal heart rates and other matrices for identifying the the challenges that a fetus might be facing. So since we can be able to take the fetal heart rate from different mothers, let's say we have mother A, mother B, mother C, and both have fetuses that are having a fetal heart rate of, let's say, 130 beats per minute. There are three, all of them have 130 beats per minute. Don't you think if we drop duplicates in such a scenario, we might kind of reduce the size of our data set and even uh, maybe not have, or rather having a challenge in coming up with the accuracy of the model? Because I was looking at it also in a perspective of maybe predicting the house uh, the house prices, let's say in a town where you find that there are different houses that have same prices. So I was just thinking, if you drop the duplicates, you might kind of affect the size of your data set. I don't know, maybe you can clarify on that.
Yeah, that's a very good one. But then, in a sense, if you came to my apartment, which has let's say we are 20 people here, all of us, the unit size is the same, metrics, what we pay, and everything. If you study me or my, you know, my unit, why would you be interested in other units and they have everything the same? You have talked about fetal heart rate, but the duplicates are records that are the same across all the variables. So why would you have them? That is the question, rather, because one record is diametrically the same as the other record. So having two records, you do not have any additional statistical value out of those two records. They contain exactly the same information, and that is, the baseline for dropping the duplicates. We had 13 of them.
Thank you so much.
Okay, welcome. So I'll proceed. Uh, Actually, from most of these box plots, we see that our data set needs some scaling. So feature the features have significantly different ranges, as shown by the box plots we have seen there. So we need some scaling. So that analysis is based on the same level for the variables. From there, we do some EDA, just a deeper understanding of our data set. So this is the data set that you're having. We have three classes. The normal has 1646 records, suspect following 292, and then the least class is pathological with 175. In terms of percentages, we have a dominant class, which is normal at 77, followed by suspect 13, and then pathological at 8%. Then we might be curious to understand the distribution of our data set for some variables. One of our variables is a histogram tendency, which is said could be skewed or normally distributed. And these are the instances that we do have. And we are plotting this together for us to get more information with the target variable, which is fetal health. So we see that the observations or the records, the classes that on the three classes we have -1, which shows that the histogram tendency is skewed to the left. This is a normal distribution, and this one is positively skewed. We have 49 records. This is based on this particular dimension of the histogram versus the fetal health. We have 49 on this negative, which is negatively skewed. We have 49 on pathological, majority is normal, and then you have 15 on the suspect. About the then on the observations that have a normal distribution based on the histogram tendency, we have 882 for the normal, we have 91 for pathological, and we have 137 for suspect. So on these cases, we see that we are having a normal, which is leading both here and here, and also across. Then we have the second last class as a pathological, but this is an insight here, whereby for this class, we have the list on suspect. So you expect the histogram tendency for the suspect class of fetus to be the list to have a negative skewness. Maybe you'll check on the visuals, have a better understanding. So here we divide our data into, we have variables that are numeric, and then we have categorical. So we are dividing so that we can use the numeric variables to plot the distribution, one of which will be the histogram. And I'll take you to the visuals. The first one is this one, where we are having the baseline value. So we have baseline value against the fetal health class. And from this, we see that on the baseline value, this color, this is the suspect, and pathological, they have higher baseline values. You can observe that based on where we start to count. This is around majorly 120 all the way to around 160. But far behind on the lower side, that's when we have the normal. So if you're observing the characteristics of a fetus, the suspect and pathological will have higher baseline values. And we have a couple of them, but I see the time is not on our side. We'll share this, and it is well commented on our GitHub. So we may not have a chance to go through all the interpretation, so I'll just go to the next step. Some of them, like this one, do not give us any insights, but when you're plotting, it's better to just plot so that you don't keep plotting one after the other. Then you choose to work with the ones that have some insights. If we had more time, maybe we would have gone through this. But these are some of the highlights where most suspect fetuses have baseline values tending towards the upper bound. That one you have seen. Another insight from the plot is that most normal fetuses are associated with normal distribution for mothers' uterine contractions, while suspect and pathological fetuses observations are skewed to the right, with pathological experiencing the highest contractions per second. So what you're supposed to do is to go up there, get to understand again what do those variables represent, where do we have a case, where do you have a concern, at what point is it a normal for a fetus, and the course of action. So we said that we need to do some scaling because our variables are not on the same standard, and this is exactly what we are going to do. Another interesting subject to consider is the correlation, and maybe probably to explain why correlation is important, and also based on the use case that is at hand. If you have a correlation is the numbers we are having here. These are coefficient of the correlation coefficients, and that is that shows the linear association between two variables. For example, I'll pick on this one, which is 0.89, or even this one that is 0.93, which is quite high. So this is the association between the histogram mode and histogram median. So the correlation is 0.93. This 0.93 is the correlation coefficient. This is a representation of the linear association between two variables. And what this means, these variables carry the same information. If they are highly correlated, you may take a threshold of maybe 90% or something. And if you're working, there's no clear cut, by the way. So if you're working with 90% and you find a variable like this, it shows that these two variables are highly correlated. They carry the same information, and that means you can drop one and work with one. The reason as why you are dropping one is that if you have two variables that are highly correlated, they are overemphasizing on one concept in your data set. And that concept will be given more weight in the whole analysis. And the results that you're going to get will be inflated. So there's no need of working with two. One way is to trim one, but a more appropriate way is to come up with a ratio so that you don't lose information. If you have these two variables that are highly correlated, you can use a ratio, one divided by the other, so that you have two variables. You do not have to drop and lose your information. You can create what we call composite variables based on the highly correlated variables. You create one variable to represent the whole scenario. So in this particular case, I work with a threshold of 0.85. So variables that are having a coefficient correlation of greater than 0.585, we are going to drop one and work with what will be left. And this function here drops that. And these are the number of variables that you are left with after dropping the highly correlated variables. And of course, it makes sense to have a histogram-based variables highly correlated because they are referring to the same histogram. So the next step is the model. So we are going to split our data into training and test. So what the training does is the data, just like the normal learning, that is going to learn about the characteristics and the relationship that exists in a data point. Then from that, we are able to predict what will happen in the future, but there are known instances. So that's where you divide your data. So that you also need to test the validity of your model on the holdout set, which we call the test. If you have 100 observations, you might take 70 to train your model with, then you hide, quote unquote, 30, such that when you have trained your model, you can try to predict the instances based on the 30 observations that you have set aside. And because these 30 instances are labeled, so you're able to test the accuracy of your model. Our data set, based on this, I have worked with a test of 30%. So the 30% of my data will be test. So 70% will be used to train the model. So on the train set, I have this number of observations, which is 1,279. Of course, the variables are the same. What we are setting aside are the rows against that test. So I have decided to hold out 634 records to try and validate the accuracy of my model. Some manipulation, data type on the train. We have histogram tendency, and based on this, we see that histogram tendency has been labeled, assigned the wrong data type. So that's why I hope it was corrected. Yeah, it was corrected up there when we run the data type confirmation. So it is object, and this one is a class. So it is a class with 3 categories. And for our model, we are going to, you have a class histogram tendency. It has -1, it has 0, and it has 1. That is a class. For you to make it numeric for the purpose of analysis, we transform it through one of the ways is one-hot encoding. So this one makes a sparse matrix out of your class. It's the same case if you are having maybe gender, male, female. You can transform that into numeric or numerical representation with maybe 0 being male and 1 being female, something of the sort, for the purpose of analysis, because the model will not take female that text and make meaning out of it. So you need to transform it. And that's what is happening here. Again, we said about our feature standardization. Our features need to be on the same scale. It's just a process or the explanation of what we mean. How do we standardize? Assuming you have a variable x, and the mean of that variable is, for example, 10.4, and it has a standard deviation of 4. How do you standardize? A value, for example, there's a random value, 15.9, based on these measures, central tendency measures of your variable. You have an observation 15.9. How do you standardize that? So you are going to take this value 15.9, you subtract the mean, then you divide by the standard deviation. So basically, that's what we mean by standardization, and that's what we are going to take through all our numeric variables. But there's a function to do that. You don't do like manually. That's just demonstrate. So here you see that our variables have been standardized, and you can confirm that using the box plot. You see our box plots are, more or less aligned, meaning we have standardized and we are on the same scale. And now the model will be ready to consume our variables and give us right predictions. How do we carry out the scaling? There is a concept that is called, or we avoid to get into, the data leakage. So if we have two data sets, we have a train and we have test. Any transformation that you're going to do, you need to do separately for train and for test to avoid data leakage. Because if you combine that transformation, that means that your model will be pre-exposed and you will have chances of overfitting or having many chances of more chances of false positive in the analysis. So you do them separately. So here we encode and scale the test features, same for the train. And we are confirming the same. We have successfully transformed our data and scaled it. Then we are now at the model level. Modeling sometimes is there is no clear single model that you can choose and work with because data sets are different. But you can work with candidate models and also based on your past experience. So for this one, I decided to consider 3 candidate models, that is CatBoost, RF, and logistic regression. And also the choice of your model sometimes is informed by the end result and the consumer of the end result. For these 2 models, the CatBoost and RF, you'll sort of be compromising on the interpretability. And I will emphasize on the concept of a box, the black box. You may not be in a position to explain the output of CatBoost and RF. So if the end goal is to have explainability, then you may want to consider logistic, because logistic, the results are explainable. So training the same, and then we'll assess the performance. On the performance, we have performance metrics. And for classification, the mostly used performance metrics are the precision, we have recall, and we have F1. So based on these, metrics, we see that on, for example, this is CatBoost. The weighted average, because we are having 3 classes, so we need to work with an average. For precision, we have 0.96, which is 96%, quite a good one. On the train, on the test, then we have a same 96 across. For precision, recall, F1, we'll come into what these results mean and when to use what metric. For random forest, we have a weighted of 95% across, and also for the logistic, Here we are using multi-class because we do not, this is a case of more than two classes. It's not binary, so we use multi-class. The metrics we are having here is 91% on precision, RICO, and F1. Then we need to do some model optimization to see if we can go beyond what you are currently having in terms of these metrics. For model optimization, you may consider to do some feature engineering. Again, this is not cast on stone. There are so many other methods out there, so you may want to have some research and know what kind of engineering that you need to do in terms of your features to get better results. So we are coming up with the first thing to check is the feature importance. We have a set of, I think, 20 variables or 21 variables. So which variables are important in our analysis? And in this case, we want to work with variables that explain the highest variability in our data set, because that is what matters. But again, about feature importance, if you find that some variables are not important, and you're not working with a person who has the domain expertise, you may not be in a position to drop features, because the variables that you retain for the analysis should be selected based on their practical usefulness or actionability potential. So you need an expert. For example, in this case, you need a medic or that skill that you show up there for you to know which variable to drop and which one to retain, even if they do not have as much importance as the model portrays here. So the
Yes.
most important, yes, yes, yes.
Do you want to take a question? Then,
Yes, yes, yes.
Ivan, please go ahead and ask.
All right. Thank you. So I have a question to Samuel. On the transformations you did some bit of scaling, and then you did some sort of a bit of encoding as well. And on the model, you've chosen RFM, and you've also chosen CatBoost. So my question is, does the kind of transformation that you do depend on the model that you're gonna use? Because if you're using any tree-based model, normally you don't really need to do a lot of scaling. And then if you probably are using CatBoost, it takes in categorical features, so you don't really have to do encoding. So my question is, do the transformations that you do depend on the model, or the model depends on the transformation? I don't know which one comes first, so that you make work easier.
Yeah,
Thanks.
that's a good question. And I start with a CatBoost. CatBoost has an internal capacity to encode to one hot encode. So if you're just using a CatBoost, even if you don't do one hot encode, it has that capacity within its algorithmic setting. But for the logistic and for the RF, they do not have that capacity. So you need to do the encoding. The reason that's why I did that, so that I just have one function that does everything for all the models. But for CatBoost, I agree with you. It's not a must that you do. I don't know if I have responded to you.
Yes. Okay. So the transformations that you did, both encoding and standardization, that was purely because of the logistic regression algorithm, right?
Logistic, yes.
Uh-huh.
RF is
Uh-huh.
not clear if
All right.
it is able to work with that. There is some research on that, but
Uh-huh.
it's not clear that independently, without the scaling, it's able to give you the same results. Because remember, how does it work? It's parallel. It's not like CatBoost. The decisions are made parallel, so you need to have the same scale for the trees, and when you're doing the pruning to give you desirable results. So that one is not quite clear, but for logistics, clearly you do have.
All right, cool. Thank you.
DS, do you have anything to add on to that? Yes.
Not really. I think that's sufficient.
Okay.
And the other aspect probably is just depends on the use case, because there are certain models that will fit a certain use case you want to do, and then also the kind of data you are working with, and the distribution of your data as well. And for this case, we are dealing with a classification problem, issues to do with the class imbalances as well. So if you find your data is imbalance, then you will need also to be keen on the kind of model you're using. Is it a model that will be able to handle the class imbalance, or you need to undertake some transformations so that the model works or gives you best results according to whatever kind of data you have at hand. Yeah, but your response was sufficient, yes. Thank you.
Thank you. So we are going to pick the most important features. Again, I said that on feature importance, the features that you consider important should be important the person who have the domain expertise. So you as a modeler, you may want to say these features are important, but at the end of the day, you need to consult the domain expertise because they know better which variables are important, the particular use case that you're working on. But we'll pick the best features statistically, but you also need to pick the best features business-wise. So there's a selection based on the, based on statistics. And I think we have more. There was a question on box plot. So we are checking these features. One of the best features or most important features we are having here, based on the score above, is abnormal short-term variability. So we are plotting that against our classes. I hope these box plots are friendly. So what we see is that in terms of abnormal short-term variability, both suspect and pathological classes have more or experience more abnormal short-term variability. We can see based on the two box plots for those two classes. Another variable that is quite important is acceleration by fetal health. No much information, but based on this one, you can see that we are having more accelerations for the normal. Maybe perhaps acceleration is a good thing for a normal fetus. We can't rule out, but the results we have suggest so. So this is not counterintuitive. Another important variable is percentage of time with abnormal long-term variability. Again, the normal has less percentage of time with abnormal long-term variability. So based on this output, we see that abnormal long-term variability is undesirable for the health of our fetus. This is just to help you understand the results above. Variability, what does it measure? These are fluctuations in FHR. Variability reflects the adaptability of fetal nervous system. So if we have a variability, we have variability variable. Yeah, like this one. So short-term variability in terms of the health of a fetus, is it desirable? Is it not desirable? And we can see those ones, whereby the normal is exhibiting or experiencing a less of abnormal short-term variability. About accelerations, which is another feature, these are the number of temporary increases in FHR. Why it matters to us is accelerations are positive signs showing feature responsiveness. So you need to have this interpretation, but mostly as a modeler, you need to work with maybe a medic for this particular case for you to have a better understanding of these variables. Because it's one thing to have a statistical understanding, it's another to have a business understanding. So we are dropping some features. This one I said is not it's not something that you every time go by. For you to drop in a feature, you need to work with a person who understands what works best for them. But here the dropping of features is based on solely statistical, implications that you are having. So we drop both the features from the test and from the train and rerun a model to see if there is any improvement. And we are dropping them separately. We say that we deal with test and train separately so that we avoid any leakage. So we train the model with the features that we see are important based on the analysis, and we test the same model. So from what we have, I did not find any changes in terms of the metrics, even after dropping the features that we considered they were not important. So we are more or less getting the same. The change is marginal, so nothing much. We noticed that 77% of our data, 77% of our observations are from one class, which is normal. Maybe perhaps we have a case like yes, alluded to of imbalance. So one of the ways to work around the imbalanced data is a SMOT, application of SMOT, which is a synthetic minority oversampling technique, trying to boost the underrepresented class. So that's one of the ways you know to try if you want to improve the results. That's what I did here. And again, no much gain because we're already talking of over 90%, in terms of the F1, the acquisition and kickoff, so no much gain. We are still having more or less the same. So some, marginal changes. The other approach is to hyperparameter tune, just walking you through the process of coming up with a machine learning model. What we are having up there are default hyperparameters. And we are saying hyperparameter because for cut boost and for the rep, these are, non-parametric. We do not have real parameters. Parameters, I mean the coefficient and the constant. We can have that for logistics, but for two other models, the cut boost and RFM, they are non-parametric. So they have hyperparameters. They do not have true parameters. And that speaks into the interpretability of the results from the non-parametric class of models. So after tuning, what changed was the weighted average. One score for rev and cut boost remained fairly unchanged after hyperparameter tuning. So the first results we got are sort of optimal. And then what we do next, we want to, you have a model, you have trained, you have tested. But then if you give it the test or the holdout set that you're having, are you able to give the predictions now in real world? If you deployed this model in a medical, field, are you able to use it, apply it, and get the predictions? So that's why it's important to try and have a sample, and this sample you can share with business because now this one is non-technical. It's just a representation of the actual versus the predicted. So there's an extract of a sample. Maybe we have some time we have it. Just a sample. Yeah. So for example, it's a sample from the test. This is the actual class, the actual status. We have this variable, fit of health, and then we predict it. For the first observation, here in the test, we see that the actual class is suspect, but the model predicted normal. So, imeuma nje. This one is normal, predicted normal, normal, normal. So such a thing. And then I would like now to get back to slides and finish up the presentation. If we have any questions.
Yeah, we have a question from Ivan. I think
Okay.
she can ask.
Right. So you mentioned during feature selection that it's a combination of statistical results and also I think domain experts. I'm just curious. I think that a lot of people right now wanting to move to data-driven decision is that there's a lot of feelings sometimes that go into making some decisions. So I'm just curious, how do you guys how do you strike the balance between the feelings from the experts and what your statistical analysis does? And then very quickly, because I know you're out of time, you mentioned mods as something as a way of handling class imbalance. Somewhere along the streets of this internet, I just saw that SMOD has been rubbished as a means of dealing with class imbalance. So I don't know if you can probably speak to that. Yeah, thanks.
Yeah, so I'll start with the last question about SMOT being rubbished. In statistics, because data science, you are coming from statistics and mathematics, unless someone is coming from a strong mathematical finding that it is not necessary, any other talk remain rubbish. Okay, sorry for using rubbish, remains rubbish. Because these are facts. Any method that you see here, any algorithm, any equation that you see here, they have mathematical underpinning. So I would ask you to go and cross-reference with other authors, find the mathematical setting of the SMOT, and then you can try also yourself to test if that is true, because there are so many things in the internet. I'm not ruling it out. It might be true, but then you need to really research and understand the mathematical setting of the uh, algorithm in terms of addressing the underrepresented classes. If the mathematical setting does not make sense, then it's rubbish. The second question is a balance between business and the model or the machine learning person. And I'll give you a case in point, a very practical case. If this model, we were using it to score, let's say in a banking field, you are scoring customers in terms of the lending. A safe borrower to lend to the defaulter. You have recall and you have precision. What does precision do? It concentrates on the positive rate, the actual. So what that means, if you work with precision, you are going to lend less. That's the model. If you work with RICO, you are going to allow more borrowers. But then you have a guy from risk. The risk want to minimize the risk, want to minimize the exposure that is there to the company. So for the risk person or for the risk department, they would be more interested for you to apply precision and just lend to a few people. Come to the business side, the marketing people who want to sell the loans. They're interested in RICO because if you use RICO, you are going to allow more borrowers, and in the process, you'll increase the rate of default. You have those two teams, and you are the machine learning person. Are you going to use the precision? Are you going to use the RICO? Which side are you going to fall? I think it's something to think about, and that is the dilemma. Also in features, business believes this is important, the model has this. So what do you have to do? I do not have a straightforward answer. I will invite Brian to maybe add on to that.
Yeah, thanks, DS, and it's quite interesting. Yeah, those are some of the issues we have to deal with in the practical setting out here, and sometimes there's no straight answer, and you get to a point whereby for the specific use case he's mentioned, it gets to a point whereby now you look at what is the risk appetite of the bank, because on either side there are gains and there are also losses. So you allow more people, you are exposing yourself. Yes, it is a risk you are taking, but in the event that the default rate is lower, then that means more revenue, more profitability. And had you not allowed more people, then that would mean you would have lent to a smaller portion of the guys who seemingly look good based on whatever metric you put more emphasis on. And now that means that, yes, you will have few guys getting the credit facilities and repaying, but then you might not be able to say achieve more in terms of if you are really keen on increasing the number of people who you are lending to, and also keen on scaling in terms of profitability and the revenues as well. So it's really a tricky balance. And so you need to really be keen on what do you want, and sometimes you take the risk. If it goes well, well and good. If it doesn't go well, you learn from that as well. And that's why whatever he mentioned as the domain expertise, over time, this person has been in that industry. He has observed the behavior of the customers who have a specific, say, trait, and they have that command when they tell you for this specific case, let's go this direction. You as the machine learning expert, you may also want to incorporate their feedback and ideas because they understand that industry. So I think I'll just leave it at that, but we just try to paint a picture of how it is out here in the real work setting. Ivan, I don't know whether that is helpful.
Yeah, that's helpful. Thank you.
Yeah, so I hope on the smooth, I'll also task myself to, reevaluate how it is, reevaluate how it is formed and how it works on the imbalance case. And maybe we can side chat later. And also, I'll be curious to get what you find yourself. Do you have any other question on the? I want to now go to the slide.
I think in the interest of time, we can cross over to the slide as we finalize, and then any further questions can be channeled through our platforms, WhatsApp, even email. The emails we reached out to you. If you have any questions, you can just respond to that specific email, and then we'll get back to you. We are also on LinkedIn, so feel free to even inbox us via LinkedIn. Thank you.
Yeah, so thank you, DS. And we had gone through this one, data understanding. We have gone into the modeling. So I just wanted you to have a taste of the notebook, the real work, because it's just slides. So what we have done after data understanding, we have done the data processing, whereby we have checked the missing values. And then we have checked the data types, then checked the duplicate, worked out detected the outliers, did the feature scaling. Then onward, we did the exploratory data analysis, whereby we found that the normal category is distinctively the majority class, and this where we are coming from in terms of imbalance. It has a total of 77. It does not mean it's a bad thing, so long as the model is able to understand that this is a majority class and is able to work on it and give you the results. So if you are able to get the results, with one class being 77% of the observations, still fine. So another thing we found from the EDA is the normal fetal health category was dominant for the histogram tendency variable. The presence of suspect fetal health category was a least for the negative one, that is the negative skewness. Another finding was that about the distribution of numeric variables, most suspect fetuses had baseline values heading towards the upper bound of the baseline value. The suspect and pathological fetuses exhibited fewer instances of abnormal short-term variability. In terms of now the business, you may not present the notebook to the business, so you need a deck. And a deck is high level, just presenting your key findings. We are familiar with this one from the notebook. Well, not dwell too much on them, these ones. I'll go into models. So the evaluation metrics that we chose were precision, RICO, and F1. So remember, it's very hard for you to decide based on precision and RICO, although it is based on what you want to achieve and the implication of working with one. So we have F1, which is the harmonic mean between precision and RICO. So if you're not able to decide, if you're okay with business, you're aligned, you may use F1. Then the candidate models that we were working with, we have a random forest, cut boost, and logistic. We went through model optimization, through data engineering, smooth analysis, and hyperparameter tuning. And our final model here, random forest and cut boost, were selected since they had a tie in performance based on the selected evaluation metrics. Again, I said that for you to choose the model, you need to have the end goal. If the idea is to have results that are highly interpretable, we may have chosen the logistic regression because that one is a parametric. You can just get the coefficients and the constant and reconstruct the results and try to see the weighting per variable. But if you just want to know to classify the fit as normal, pathological, and the other class, you may decide to work with a ref, cut boost, and others. So not only 3 models, we have so many models. The choice depends on the use case at hand. So key findings that we have about the predictive features. The analysis has revealed that certain features such as abnormal short-term variability and these other ones are the most important for predicting fetal health. So again, we say this will depend on the domain expertise. About the model performance, after thorough evaluation and hyperparameter tuning, the analysis found cut boost and RF as the best performing models for predictive fetal health, achieving an impressive F1 score, which is the harmonic mean between the RICO and precision of 95%. What are the healthcare implications? Because again, these models are supposed to work in the healthcare industry. Are we improving the status of the industry by deploying machine learning models? And we see that CTG facilitates early detection of fetal distress and congenital heart defects, enabling timely interventions to prevent irreversible harm. CTG can play a crucial role in reducing fetal mortality rates. And then integrating of predictive models based on CTG features enhances healthcare decision making, safeguarding maternal and neonatal well-being. What do we recommend? And again, we are in the two twist, so I'll not dwell on this one because I have highlighted Brian has emphasized the seesaw kind of a thing. Where you have precision, you have RICO. If you use RICO, that means you are going to allow some false positive, meaning you may subject a fetus to treatment even though it is normal for it being misclassified as suspect or pathological. The question is, what is the implication of that? if you subject a normal fetus to treatment, what is the health implication? If there is no, negative impact, then you may work with RICO and subject as many fetus to, treatment. On the side of precision, we are going to have instances where a suspect or pathological fetus will be missed out, will not be, mapped out for attention. If that is the case, and you leave a fetal that is suspect, that is suspect or pathological, fail to treat them, what is the implication? So again, this is where the domain knowledge comes in. Do you go with RICO? Do you go with physician? Depends on the understanding from the medic. And maybe case in point would be maybe if this was supposed to be deployed for detection of cancer, and you have a false positive, whereby you take a patient wrongly, quote unquote, through chemo, and they were not supposed to go through that. The implication is, unimaginable. If you have a COVID case and you predict that someone, has signs of COVID, even if they did not have, and the only treatment is isolation, other than, the lost labor, nothing much, where when they are in isolation. So it's case by case. Another one is the, credit case, the default versus good borrower case. So this one is something that there is no clear yes. How do we obtain the data for a model in, a clinical setting, kind of an environment? And we say that in this case, we base the data collection on the clinical activities, because clinical actions are mapped by the clinical activities. The application of an AI, system must ultimately support clinical practice and be driven by clinical problems. In such an ecosystem, you would start with clinical activities, whereby there could be some screening, diagnosis, and treatment. Then, in these activities, you would generate some data. And this data would be in terms of, the notes, the clinical notes that, nurses, medics take. Then, you can take that through an NLP to have an understanding. And the output you get there would maybe to suggest you need further treatment or further analysis, and you might be referred to maybe the imaging, the EP, and these systems will also generate data. Then again, that data will go into machine learning and predict, do you have a condition or you do not have? Is there a cause for alarm or you're just okay? So this again will come to clinical activities again, maybe re-screening, diagnosis, and treatment. It's kind of circular thing, just to expose you to AI system for clinical data production and analysis. If our model, we were supposed to deploy our model, but we got maybe the RF, the cut boost, or even logistics, if that was the model of choice. What processes do we go through? The first process of the model is, of course, data collection. This will be report, patient characteristics from training data, create data sets, and all these things. Then we have phase 2, which would be model development. This is what we have done. And then we have also done the model evaluation in terms of the success metrics of our model. Once you do that, the model goes through authorization. Authorization comes before deployment, so that the model is certified, it's good to be used by the client. And then what is a good model? What is a good AI model? A good AI model should be reliable and accurate. For you to trust the results, they have to be reliable and accurate. Robustness. Is your model able to respond to changing scenarios, even when you have a data change? Is your model able to stand that test? Again, is transparency, and I'll insist on this transparency. We had 3 models, but if you are going for transparency, the model you'd have chosen maybe is logistic because it's transparent, it's explainable. You also need to consider the fairness and equity, safety and privacy. In this case, it's the safety and privacy of patients' data, and then the model should be fit for purpose. And that is the end of my presentation. I don't know if there are any questions.